Hello, I'm Álvaro Calafell and this is the second video about the harmonic problem solutions. This video presents filtering equipment as a solution of electrical installations. In previous videos about harmonic problem solutions, I presented a guide for choosing the best solutions and introduced particular solutions in electrical installations. In the present video, I will explain filtering equipment. According to the 16th video, the harmonic problem solutions can be divided in those applied to installations and nonlinear loads, and those applied to compensation equipment. In the present video, I will explain some solutions related to installations and nonlinear loads. In particular, I will present the harmonic filtering solutions to reduce the harmonic currents injected by nonlinear loads. Filtering equipment can be mainly divided in three kinds of devices. The choke inductances, which are a cheap way to reduce the harmonic currents of high polluting devices. Isolation transformers, which are a relatively expensive way to reduce the harmonic currents of medium polluted devices. And active filters, which are an expensive but very effective way to reduce the harmonic currents injected by aggregations of low polluting devices. It is important to recall the most influential parameters on the harmonic currents consumed by the nonlinear loads. These are the consumed active power and the harmonic spectrum of these nonlinear loads. Therefore, the value of both parameters must allow to decide which is the best filtering equipment to be used. In general, we use individual filtering at low level for high power nonlinear loads. Collective filtering at secondary distribution panel level is used for medium power nonlinear loads. For aggregations of low power nonlinear loads, collective filtering at main distribution panel level is used. However, the harmonic spectrum of nonlinear loads must also be considered to decide the harmonic filtering equipment to be used. Only the harmonic currents of nonlinear loads with power consumption higher than 75 kW will be mitigated with filtering equipment at low distribution panel level. Choke inductances will be used if the total harmonic distortion of these currents is greater than 20%. Otherwise, isolation transformers will be used. The goal of this filtering equipment will be reducing the harmonic currents of the high polluting loads in order to turn them into medium polluting loads. The aggregation of nonlinear loads with power consumption between 15 and 75 kW will be mitigated with filtering equipment at secondary distribution level, and depending on the harmonic distortion of the consumed currents, choke inductances, isolation transformers, and active filters will be used. The aim of this approach is to turn the aggregation of medium nonlinear loads into low-polluting nonlinear loads. Finally, the harmonic currents of the nonlinear loads which have been mitigated at different levels of the installation can be reduced by means of active filters at the main distribution panel. These harmonic currents would not have a high value in order to avoid expensive active filters. The following table summarizes a classification of nonlinear loads depending on their active power consumption and their total harmonic distortion. The table also presents the different solutions to be applied to reduce the harmonic currents. Uninterruptible power supplies and variable speed drivers are mainly nonlinear loads with power consumption higher than 75 kW, which must be filtered with choke inductances and isolation transformers at load panel level. These loads, together with air conditioning equipment, can also be loads with power consumption between 15 and 75 kW, which are filtered with choke filters, isolation transformers, and active filters connected at the secondary distribution panel level. At last, low consumption nonlinear loads are the previous nonlinear loads with filtering equipment as well as lighting and industrial equipments. The currents consumed by these nonlinear loads are reduced by means of active filters connected at the main distribution panel. The following diagrams show several examples of choke inductances and how they change the original current waveform, reducing the nonlinear load harmonic spectrum. We can observe that this harmonic spectrum is reduced from high to medium values of the harmonic current. The choke inductance to be installed is selected from the manufacturer catalog by means of the rated voltage of the installation and the root mean square value of the current consumed by the nonlinear load. The voltage and the current of the choke inductance must be equal or greater than the voltage of the installation and the current consumed by the nonlinear load, respectively. The value of the inductance in the following table corresponds to a voltage drop in the inductance of approximately 3 to 5%. For example, for a choke inductance of 1 mH and 45 amperes, the voltage drop in this inductance becomes 6.1%. The following diagram shows another type of choke inductance, as well as the change in the waveform of the nonlinear load consumed current. It is noted that the new waveform becomes more sinusoidal with the choke inductance. To select this type of choke inductance, the voltage and the frequency of the installations, as well as the root mean square value of the currents consumed by the nonlinear loads, are required. As previously commented in other slides, this choke inductance can be connected at the low panel level and at the secondary distribution panel level to reduce the corresponding harmonic currents. The next slide shows the use of isolation transformers. The aim of isolation transformers is to block specific harmonic currents depending on the transformer's connections. For example, the transformer configuration on the left blocks the fifth harmonic, whereas on the right, the triple harmonics are blocked. To select this transformer, the nominal voltage of the installation and the apparent power of the loads by the transformer are required. The use of these transformers is not common, since they are more expensive than choke inductances, which in general are enough to reduce the harmonic currents until the required level. Active filters are the most effective but also most expensive filtering equipment. It measures the load current, removes the fundamental current, and injects the remaining harmonics 180 degrees out of phase to eliminate the harmonics completely. It can also be used to compensate reactive power of a load. The active filter modifies the response according to change in the nonlinear consumed currents, and therefore they can compensate harmonics and reactive power instantly. They can be connected at any level of the installation for single, partial, and total compensation. But the most common distribution level for it to be connected is in the main distribution panel, in order to mitigate the harmonic currents consumed by the aggregation of nonlinear loads. This should be done after applying the other filter equipment, in particular, choke inductances in other distribution levels to reduce the harmonic currents of the high-polluting nonlinear loads. Active filters are selected from manufacturer catalogs by means of the rated voltage of the installation and the harmonics and the reactive currents to be compensated. The total current that active filters may inject is calculated from both the reactive and harmonic currents using the following expression to select the most appropriate active filter. As an example of active filter design, consider a 400-volt electrical installation which supplies nonlinear loads consuming this total current, with this total harmonic distortion, and the power factor equal to 0.85. We would like to compensate the harmonic currents and the reactive power until a power factor of 0.98. Taking into account the electrical concepts reviewed in videos 5 and 6, the procedure for harmonic filter design is the following. First, from the root mean square value of the total current and the total harmonic distortion, the fundamental current root mean square value of the total current is obtained. Then, the harmonic current root mean square value can be obtained, which should be the current to be compensated by the filter. Subsequently, the fundamental power factor of the load is calculated from the total power factor and the distortion factor. This fundamental power factor allows to determine the reactive power and therefore the reactive current to be compensated. Note that after the harmonic compensation by the filter, the total and the fundamental power factors are the same. Finally, the rated current of the filter should be 91.5 amperes if used to compensate harmonics and reactive currents, or 66.7 amperes if only used to compensate the harmonic currents. These rated currents are multiplied by a security factor. If we choose the first option, a 300 amperes active filter must be selected. If we choose the second option, a 100 amperes active filter will be selected. Other solutions to mitigate harmonic currents consumed by nonlinear loads are the filtering equipment installed inside of the nonlinear loads, such as sealess and active front technologies. These loads are improved nonlinear loads with a lower harmonic spectrum as seen in the plots below, by comparing them to the typical current consumed by a three-phase rectifier. The next slide illustrated a nonlinear load with an active front which uses IGBT power electronics to reduce the consumed harmonic currents.